You have to know exactly what's going on in order to even write a computer program to do that, to do the simulations in the free download of the Binary Mechanics Lab software. So if you like to tinker around, get that software, okay? Now let's look at the rest of the story. I said all we needed was the system state. We did it. Now let's do the time development, which is the bit function change over time. We have 4-bit operations, which are analogical to the operators in 20th century outdated quantum mechanics. 4-bit operations defined, and that's all we need to make our universe, along with applying these operations in a particular order. When we quantize everything, the infinitesimal increments used in the old-fashioned 20th century quantum mechanics are not applicable anymore. Everything is quantized. There are no infinitesimal increments anymore, okay? So what antiquated quantum mechanics called operators are called bit operations in binary mechanics. With reference to the relativistic Dirac equation, we had to move into our quantized world and represent momentum in the unconditional bit operation, which is really simple. It's simply shifting the bits so that within the spot unit, the state of the M loci becomes the state of the L loci. So what happens to the M loci? Well, it equals the prior spot unit carry bit, which is L sub x here, so that the state of that carry bit, L sub x, becomes the state of the M loci in our spot unit. In this diagram, we show in one dimension the unconditional bit operation with some sample data at time equals 0. And notice that at time equals 1, the M and L quanta shift in the L direction. The L direction in this example is to the right, so that this 1 goes to there, this 0 goes to there. That's why it's called unconditional, because it just happens. The scalar or electrostatic bit operation. First, we can define the scalar potential, phi, as the state of the locus M sub j. In this diagram, we can define 2 types of arrangement of spot units, which are the concurrent, which are going in the same direction, and that applies for the scalar bit operation, where our potential is mj, which is right next to the quanta that will move to the L position if mj is in the 1 state. Now the product, or and function, of E phi is a Lorentz force component and is simply the and function or the product. You notice those are the same things, and function and product, and so that product is going to equal 0 or 1. So now we can define the scalar force, which is the and function of the source loci M, the adjacent concurrent loci M sub j, times 1 minus L. What in the world could that be? That's not L. It means that the L loci in the same spot unit as the source is empty, so it can receive a 1 state moving into it. This last 1 minus L component in our 3-item and function for the scalar force is required because, as we've said, a particular locus can only contain 1 quanta at a time. If it could contain more than that, then we wouldn't have really reduced things down to the fundamentals, where a Spatl cube locus can only contain 1 or no quanta. In other words, be in the 1 state or the 0 state. So if the scalar force F is 1, then the 1 state in the M locus is moved to the L locus at time equals 1. The vector bit operation is quite similar to the scalar bit operation. In this case, we take the Lorentz force component, the A vector, in one dimension, which is shown here as L sub k, and that can equal 0 or 1, and that is our magnetic field. So this illustration shows the M source and the potential L sub k in the countercurrent location, right next to the source one-state quanta. And there are different permutations of that situation shown here. In similar fashion to the scalar bit operation, we now have the vector force is the product of your source, the L sub k vector potential component, and an empty destination L-type loci. The scalar and vector bit operations are shown in examples here. At time equals 0, the input sample data is shown for the scalar potential phi and the one-dimensional component of the vector potential A from the Lorentz equation. And you can see that at time equals 1, if all the conditions are satisfied, you're going to move the source one state to a destination L-type locus here. And the same thing occurs in the example shown for the vector bit operation. People can ask, is binary mechanics a sort of field theory? Well, yes. We have defined that all of the M loci are the electric field. Not all elemental volumes of space have an electric field. Only those that have one state M-type quanta energy. That really simplifies things because we don't need an infinite number of points in any arbitrary spatial volume. All we need is our elemental volumes defined by the primary length constant in binary mechanics. Thank goodness. And then the second kind of field, so there are only two kinds of fields according to the basic equations. The distribution of the A vector component is the magnetic field. And by the way, it seems that these are also the long sought after magnetic monopoles. Eureka! Everything in the first three bit operations occur in one dimension, so that when we are running our universe or running our computer simulation program, it doesn't matter which spatial dimension, X, Y, or Z, we compute first, because what occurs in these 3-bit operations is independent of the other dimensions, so we can do them one at a time to get the new state of our world. The strong bit operation is different, however. It deals with the transfer of one state within a spot. We call that intraspot. So the strong force has a source one state in one spot unit. Its potential is actually a neutrino, which is the other locus in that source spot unit. This is really weird, isn't it? And of course, the same thing as we had before, a empty destination locus. And when all three of those things are true, then the strong F equals 1, and we get a transfer from the source spot unit of a quanta to the destination spot unit. Now, the strong bit operation is disabled by what we call inertia. We define inertia, P, as the product or and function of the M and L loci in a spot unit, and that can equal 0 or 1. In this case, it equals 0 because the black arrow shown here at time equals 0 is in the one state, and the empty circle here is our M locus in the 0 state. If P equals 0, the L-type quanta, the black arrow, in the X spot unit at time equals 0 moves to the Y spot unit in the M-type quanta position at time equals 1, as shown here. If inertia P equals 1, the black circle and arrow, shown here at time equals 0, the L quanta does not move from the X spot unit to the destination Y spot unit, so that we see no change here. In that case, in the next unconditional bit operation, what's going to happen? This one state quanta here will shift out to the next spot, which is shown in red up here. Boom, it goes on out. That is the mechanism of all particle motion. So you see, the strong force really is like payday. So now we have the mechanism of motion where one state quanta can leave a spot or a particular elementary particle location, that's what a spot is, to another spot, which is another kind of particle location, two ways: by the unconditional bit operation or when the strong force is disabled, as shown in the lower part of this diagram. Now, with chirality, in other words, the right-handed and left-handed nature of our 8 elementary particle locations, intraspot transfer of a one state that I've been talking about can either go one way or the other. And so that the D here in the destination, which must be empty, is computed with equation 16 to be equal to N or P for the left or right spots. In other words, the direction of the shift between one dimension and another in the strong force depends upon the handedness of the spot itself. It's really that simple. Finally, is the question of bit operation order. How do we run our universe? It's like a looping computer program. And in this case, what equation 17 says, that the bit function, in other words, the system state, at time equals 0, we apply the scalar bit operation, then the unconditional bit operation, the vector bit operation, and F representing, in this case, the strong bit operation, so that at 4 ticks of our primary constant time, we have a new system state, a new world. And that is how simple a theory of everything can be.